This is the fourth and final video for activity 3.1. So for this exercise, we're given a table. I like to actually use this table on quizzes and tests because they're asking you to do a lot with a little bit of information. So for example, we're given a function, h of x equals 1.08 to the x, and we're asked to identify the base, the growth or the decay factor, the x-intercept, the y-intercept, the horizontal asymptote, and this identify if it's increasing or decreasing. So the base is simply the number that's attached to the exponent. So in the first case, we have 1.08, 0.75, 3.2, and a quarter, right? If it's greater than 1, we know it's growth. If it's less than 1, but greater than 0, we know we have decay. For x-intercept, they're all going to be none. None of these will cross the x-axis. For the y-intercept, they're all going to be 0, 1. Right? When I substitute in 0 for any of the values of x, I'm always going to get 1 for an answer. Right? Anytime we plug in 0, anything raised to 0 is always going to result in the answer of 1. The horizontal asymptote for all of these will be y equals 0. And if we have growth, the function is increasing. If we have decay, the function is decreasing. So I was able to copy this table. I had a little trouble with the formatting, so please excuse my formatting issues. So you can see what I mean by formatting issues. Okay, so for our base, we had 1.08, 0.75, 3.2, and 1/4. That's just simply the value that was attached to the exponent. Was it growth or decay? Well, we have b equals 1 or greater, or really greater than 1, we have growth. Here my b is between 0 and 1, so it's decay. My b is bigger than 1, so we have growth. B is between 0 and 1, so we have decay. For all of these functions, there's no x-intercept, right? None of these, if you graph all of these, none of them will cross the x-axis, and they all have a y-intercept of 0, 1. Right? Every time I plug in 0 for x, I always receive 1 as my output. The horizontal asymptote, well, that's going to be y equals 0, right? That's the number that the equation of the line that we get very close to but never actually touch, right? So y equals 0 is this imaginary line that we get very close to but never touch. And if you graph all 4 of these, you'll see we get very close to that y equals 0. In terms of is the function increasing or decreasing, well, if we have growth, we know it's increasing. If we have decay, we know we have decrease, and so on. So if my b is bigger than 1, it's growth and it's increasing. If my b is between 0 and 1, it's decay and decreasing. And that's pretty much what I want you to take away from this table. 2 more tables that come up quite often would look like question 16. Right? Look at the output and determine if the data is linear or exponential. If it's linear, give me the slope. If it's exponential, give me the growth or decay factor. So a quick way to tell if something is linear is if the differences are the same, successive differences, meaning if I subtract 16 minus 12 and 12 minus 8, if I get the same answer, we know it's linear. If I divide 16 by 12 and 12 by 8 and 8 by 4 and get the same answer, then we know it's exponential. Okay, so let's write that down. So I just wanted to write this down. The table is linear if successive differences are constant. By the way, that difference would be the slope. The table is exponential if successive ratios are constant. Note that ratio is going to be the growth or decay factor. And if b, right, the ratio is greater than 1, we know it's growth. And if the ratio we find is between 0 and 1, we know it's decay. By the way, the word ratio, that just means division. Okay, so let's look at our first table. The first table, if I subtract 16 minus 12, I get 4. If I subtract 12 minus 8, I still get 4. And if I subtract 8 minus 4, I get 4. So you see the differences, right? These are successive differences, right? The subtraction between 2 numbers that are next to each other. 16 minus 12, 12 minus 8, I get 4 every time. So going back to my definition, If the successive differences are constant, so we know the slope is 4, right? So it says for the linear set, determine the slope. So we know it's linear because our constant difference is 4. So therefore, our slope is 4. Right? So we'll say m equals 4 for the first table. Now we look at the second table. If I subtract 256 and 64 and 64 and 16, I do not get the same difference. Right? When I try my successive difference test, you see my differences are all different. So I know this is not linear because my successive differences are not constant. So why don't I try successive ratios? You notice when I do successive ratios, or I divide the numbers that are next to each other, I end up with the same answer. I get 4 every time. And looking at my table, right, it says the table is exponential if successive ratios are constant. And in this case, if b is greater than 1, that's our growth factor. If b is between 0 and 1, that's our decay factor. Oops. So this value 4 is my b, and that would be growth factor. So I would say the second table is exponential, and my growth factor is 4. That concludes activity 3.1. Thank you for watching.